You have the audio on, yes.
Yeah.
Okay, usually I hear a message.
Can you hear us from remotely?
Yes.
Okay, thanks.
If it's recording, it should. Yes. Okay, good afternoon. Our speaker today is Kosuke Nishivaki, who got master and PhD from the University of Tokyo. Then he got a postdoc at the Japanese Center for the Promotion of Science in Chiba. And in October of last year, he moved to Bologna for a postdoc fellowship at the Radio Astronomy Institute of Ina. And he had already several papers on the modeling of cosmic rays and neutrinos from clusters of galaxies. And the stage is yours, please.
Thank you very much. Good afternoon, everyone. My name is Kosuke Nishivaki. Today, I'm going to talk about cosmic rays in galaxy cluster. Sorry, maybe you are feeling enough about this topic this week, but this is the last time, please. Okay. So, my topic is about relativistic particles in galaxy clusters. So, what I'm doing is, so this is our goal. So, we want to understand the cosmic ray physics in intercluster or intergalactic space. So, intercluster or intergalactic space means for example, this is a large-scale structure of the universe. We can see many galaxies in the universe, and there is also relativistic particles in between those galaxies. We know we can directly observe the cosmic rays in our galaxy, but there is also relativistic particles in between galaxies. And more specifically, I want to study in cosmic rays intracluster medium, which means inside the galaxy clusters. So, as an example of cosmic ray physics in galaxy clusters, I consider these topics. For example, what is the origin of cosmic rays inside galaxy clusters? For example, we can assume that this kind of jets or AGN activities in massive galaxies inject cosmic rays into intracluster medium. And also, there is a feedback process from galaxies. For example, galactic wind is a most prominent phenomena from galaxies, starburst galaxies. And these kind of activities can inject cosmic rays, relativistic particles inside galaxy clusters or intergalactic space. Well, the other possibility of cosmic ray acceleration is a shock wave. If we simulate galaxy clusters in hydrodynamic simulation, we can see very large shocks surrounding galaxy clusters, which is accretion shock. This might accelerate cosmic rays very efficiently. And also, there is a shock inside galaxy clusters, basically caused by merger between galaxies. This also accelerates cosmic ray particles. Well, turbulence is another important factor of cosmic ray acceleration. This kind of turbulent reacceleration is basically very inefficient, but if there is a seeding population of cosmic rays, relativistic particles, then this kind of turbulence is very important to reaccelerate those seed population of cosmic rays. And also, I want to study the propagation of cosmic rays inside galaxy clusters. For example, diffusion is one of the most important processes inside our galaxy, and may be important for cosmic ray protons inside galaxy clusters. Well, there is a big flow of intercluster gas inside galaxy clusters, which affect cosmic ray particles inside the galaxy clusters. So these are examples of cosmic ray physics inside the galaxy clusters. So I want to make a comprehensive, well-understood picture of cosmic ray physics inside galaxy clusters, and possibly in large-scale structures such as filaments. So let me start from the summary of my talk, which is I'm going to explain these kind of topics later. We study reacceleration of cosmic rays in galaxy clusters in numerical way. So my study is a theoretical work, using MHD simulation plus Lagrangian tracer method. We solve Fokker-Planck equation, which is one of the keywords of this talk, for 10⁵ tracers in galaxy cluster. And we consider reacceleration and also hadronic process of cosmic ray protons. By comparing the result of those calculations with observation, we can constrain the amount of cosmic protons inside galaxy clusters, and also we can discuss the mechanism of reacceleration. I'm going to present two examples about this topic. One is spectral index distribution in the radio image, and also the point-to-point correlation between radio and X-ray intensity. Okay, so let me start from the very basic introduction of diffuse radio emission inside galaxy clusters. So this is a X-ray view of galaxy cluster. So colored one, which means like a seemingly point one's galaxies inside galaxy clusters, and the X-ray emission is colored with blue. We can see the diffuse X-ray emission in between galaxies, which means there is a very hot gas between galaxies. So, and importantly, those gases are more massive, more important than the galaxies inside the galaxy clusters. If you see this galaxy cluster in radio wavelengths, you see like this. So you can see very spherical halo-like structure in the central region, and also there's an elongated filamentary structure, which is called radio shock or radio relic. This radio emission is produced by relativistic particles, especially relativistic electrons. So this means galaxy clusters are filled with relativistic electrons and also magnetic field. So this is synchrotron radiation from relativistic electrons. There are several kinds of diffuse radio emission in galaxy clusters, where, for example, the most basic one is giant halo. And sorry, no, I cannot tell this. Okay. The other elongated structure is a radio relic, and there is also a small halo compared to giant halo, which is termed as mini halo. And also recently, local observation discovered bigger halo, which more bigger than the giant halo, which is termed as mega halo. So there are two important characteristics of these kind of structures. One is very big. Its size is very big. So I will explain why this characteristic is important. And also the other one is a correlation to the dynamics between galaxy cluster. So basically, giant halo is found in merging galaxy clusters, dynamically disturbed galaxy clusters, and mini halos are found in relaxed, non-merging galaxy clusters. Well, this picture is now changing, but this is a basic understanding of those diffuse emissions. Well, there is another type of several other kinds of diffuse structures depending on its shape and size. For example, this is a bridge, so-called radio bridge, found in between two galaxy clusters. So this seemingly two galaxy clusters are now going to merge. But before this merger, we can observe some diffuse emission in between those galaxy clusters. So already there is some acceleration of relativity particles happening in between those galaxy clusters. So, okay. So I'd like to explain why the size of this radio emission is important. So so if you want to model these diffuse emissions in theoretical way, you need to consider the cooling time of relativistic electron. So this is a very famous, well-known problem in radio halo, which is slow diffusion problem. This is simply the cooling time scale of radio emitting particle is much, much shorter than the diffusion time scale required to produce this big radio emission. If you assume some single spot injection and diffusion, consider diffusion of relativistic particles, then it takes longer than the age of the universe. But the cooling timescale of relativistic electron is much, much shorter. It's about 100 mega year or so. So this is one of the big problem in the modeling of radio halo. And later I'm going to talk about the solution of this problem. So the other important point is the correlation between merger and radio emission. So left panel shows the disturbance of cluster and its correlation to the radio emission. So basically colored point, red point shows the cluster with radio halos. And if the cluster is populated in lower right side, the cluster is more disturbed. So there is a moderate correlation between radio halo and margin clusters. And the right plot is more clear. So in this plot, they shows that this is a correlation between cluster mass and radio emission, but there is apparently two populations. One is shown with arrows, which means the upper limit on the radio emission, which means non-detection of radio halo. The other population is the cluster with radio halo, apparently. And actually, we can see some galaxy clusters with radio halo and without radio halo in almost same mass range. So there is some kind of switch to make those kind of radio halos. Apparently, this is merger. So there is a connection between cluster merger, which is happening in very big scale, megaparsec scale, and acceleration of cosmic particles, which is in physically happening in very small scale. So to model this kind of radio halos, there was a decades-long debate between those two models. So one is the reacceleration model, which is where we consider turbulence and the reacceleration of cosmic rays by turbulence, interaction between cosmic ray particle and turbulence. The other one is a secondary electron model. In this model, we consider cosmic ray protons first, and the cosmic ray proton react with the thermal protons inside galaxy clusters. They collide and produces secondary particles that produces secondary electrons, and the secondary electrons produce radio emission. That is a secondary electron model. There is pros and cons in those models. For example, in the acceleration model, it is more clear that slow diffusion problem is solved by in situ acceleration by turbulence. So the merger causes turbulence inside the galaxy cluster almost everywhere. And that turbulence can accelerate cosmic ray particles inside the galaxy cluster everywhere inside the galaxy cluster. So we can naturally make big size radio emissions. And also the connection to the turbulence merger is more clear. The merger is the cause of the turbulence. And there are important tests of this model, which is where, there are many kinds of mergers. Maybe the merger between big cluster and a small cluster, which is not energetic enough, and very weak reacceleration happens in such mergers, then that makes a very steep spectrum. So, which means reacceleration is not efficient enough to make a very flat spectrum. So this is a very important test of reacceleration model. And also we have a method to measure indirectly turbulence inside the galaxy clusters using the line width in X-ray observation. This can be also an important test of this model. On the other hand, secondary electron model, which assumes the cosmic protons inside the galaxy clusters, where it possibly solves a slow diffusion problem, because diffusion cosmic protons much higher energy than cosmic electrons, so it can propagate much faster than cosmic electrons. So if you inject cosmic protons in very central region of galaxy clusters, you can make a big radio emission using PP equation. And but it's a little bit difficult to explain the bimodality or correlation to mergers, because maybe the injection mechanism is not directly connected to the merger of galaxy clusters. So yeah, we can assume some model about this, but it's not straightforward to explain these characteristics. And there is a very clear test of this model, which is a gamma ray or neutron emission from galaxy clusters, because PP collision produces mesons, pi mesons, which decays into the muons, charged pions decay into muons and produces mu neutrinos. And non-charged pions decays into gamma rays. So if we detect gamma rays from galaxy clusters, well, okay, this might be coming from the cosmic ray protons inside galaxy clusters. And as you know, the result is non-detection of gamma rays from galaxy clusters with Fermi sensitivity. So this is a Fermi observation of gamma rays from galaxy clusters, many galaxy clusters. But basically, the gamma rays are not detected from those galaxy clusters. And we can put some constraint on the cosmic ray proton amount inside the galaxy clusters. So well, those pictures represent that constraints, and if it depends on the model of synchrotron emission, because synchrotron emission depends on the amount of cosmic electron and also magnetic field. If we change the amount of magnetic field, then the constraint changes. But we can measure this from the rotation measure observation. So we can assume that magnetic field inside the galaxy clusters basically around a few micropulse, but if there is a strong constraint on the gamma ray and also very bright radio emission, then we need very strong radio emission, very strong magnetic field to explain radio emission in hadronic model. So this is a big gap between the gamma ray observation and radio emission. So basically, this suggests that secondary model is a bit difficult to explain galaxy clusters, radio emission in galaxy clusters. But there is some type of detection from galaxy clusters, especially from coma cluster, where they claim that there is a excess of gamma ray from the region coma cluster, and where it might be coming from the cosmic ray protons inside galaxy clusters, but it's a bit not how can I say, it's not consistent with pure hadronic model of radio halo. So we need some modulation in the secondary electron model. For example, we need further deacceleration of secondary electrons, or maybe there are some primary electron population in this model. So, okay, it seems like this kind of gamma ray observation has this fight between those two models has ended due to the non-detection of gamma ray observation. But it's a bit curious because, as I explain later, cosmic ray protons should be residing in galaxy clusters because they are not cooled by radiation. And well, more naively, if we observe cosmic rays nearby us, the flux of cosmic ray proton is much larger than cosmic ray electron. So inside our galaxy, at least inside our galaxy, there are much more protons than electrons. But inside galaxy clusters, we have basically electrons and non-detection protons. So this is a little bit curious. So this is my interest. So basically, I need to summarize this introduction. So the acceleration model works very well up to today, but we need to work on more about this model. So I think there are some three directions of update of this model. One is cosmology, including some cosmological discussion. For example, we can observe radio halo in galaxy clusters, and also radio breach between galaxy clusters. And how about filaments in the large-scale structures? And what is the connection between the cosmological evolution of galaxy cluster itself and acceleration particles, which is a big question. So how and when the cosmic rays are provided inside galaxy clusters and large-scale structures? And the other direction is including protons. Basically, reacceleration model, some reacceleration model include protons, but it's not extensively studied in this direction, where maybe there is a gamma ray detection from coma cluster, and we can assume that jet inject cosmic ray protons, at least from many mechanisms, such as, for example, jet propagating galaxy clusters, and that velocity share can accelerate cosmic ray protons, even if jet is composed of electron and positron. So there must be some cosmic ray protons, and also galactic wind can inject cosmic ray protons. So we need to include cosmic ray protons in very serious way, and we need to update the acceleration model. The other one is we can go into very small scale, and we can discuss some very exact mechanism of the acceleration, which is interaction between MHD wave and particles. So how, now it's 23 minutes, okay. Okay, so I need to speed up. So, okay, I like to explain very important parameters in the acceleration model, which is cooling timescale and reacceleration timescale. Well, basically, this is a order of 300 mega years determined by the energy of relativistic electrons, which we can assume this energy from the value of magnetic field. So if we know the value of magnetic field, we know the observing frequency, and we can guess the energy. And there is a cooling due to the synchrotron radiation, inverse Compton radiation, which leads to this time scale. And there is a big gap between this time scale and the lifetime of radio halo. We can guess the lifetime of the radio emission. Okay, the merger induces radio emission and how long it lasts. We can guess this time scale from the population of radio halos. So this is basically an order of a few to several giga years. So there is a one order of magnitude gap between those two time scales. So macro time scale and micro time scale, there's a big gap between those two time scales. And this is particularly important if you include cosmic ray protons, because if you assume reacceleration by turbulence of cosmic ray electrons, cosmic ray protons should be accelerated with the same method. And cosmic ray protons are not cooled by radiation. So for this long time scale, this very efficient reacceleration mechanism accelerates cosmic ray protons so very efficiently, and the spectrum becomes so very is not unique and normal one. It's a very unique spectrum. But this is a little bit in detail, but there is a microscopic explanation of the acceleration model. This one is transit time damping. This is interaction between compressible wave and resonant interaction between compressible wave and cosmic ray particles. But currently, many people are assuming non-resonant interaction between alphaphenic, which is solenoidal turbulence inside the galaxy cluster. And basically, both mechanisms can explain the time scale of 300 mega year. Okay, so this slide is important. So, okay, what I'm doing is solving this equation. So I'm solving Fokker-Planck equation, which is for to get the phase space distribution of cosmic ray particles. So distribution in space and also momentum. So this equation includes many important physics related to cosmic rays, for example, cooling and reacceleration and diffusion and PP collision, of course. We solve this equation for both cosmic proton and electron. So we can follow the spectral evolution of those two particles. Yes, so we numerically solve this equation. What we get is, for example, this kind of spectral evolution of cosmic ray proton and electrons. If the deacceleration is switched on, the cosmic ray electron spectrum evolves into higher energy, and that can explain the very steep curved spectrum of radio halo. So basically, this is what I am doing. And sorry, this is a little advertisement of a paper I did in Tokyo. I already did some calculation, including both reacceleration and secondary electrons. I already discussed about the constraint on cosmic ray protons only using radio observation. If there is a population of cosmic ray protons, even if it's very small, we can see some difference in the mass radio power plot. And this can be used as a constraint on the injection rate of cosmic ray protons. And we find that this constraint on injection rate of cosmic ray proton is very, very deep, very, very severe, which excludes some injection model of cosmic ray protons. So, well, yes, we can compare some models, including secondary electrons and without secondary electrons. And this is what I mean by a very unique spectrum of cosmic ray protons. And maybe we can check if, in extreme case, we can check this by neutrino observation or gamma ray observation. If we use a stacking analysis of neutrino observation, we can exclude this kind of very steep hard spectrum of cosmic ray protons inside galaxy clusters. And finally, I'm going to explain my preliminary results using MHD simulation plus Lagrangian tracer method. Well, yeah, okay, this slide is not important, but in next decade, we observe galaxy clusters more in detail, in more wider frequency range, and also more fine spatial resolution. So we need a very detailed model of radio halo. Okay. So we use MHD simulation, high resolution MHD simulation. And as a post-process, we calculate the tracer particles inside those galaxy clusters. So basically, these particles follow the velocity field of baryonic matter inside galaxy clusters. Along this trajectory, we solve that Fokker-Planck equation. So we solve the spectral evolution of cosmic rays along this trajectory. So this is an example of the tracers simulated in MHD simulation. And shown are 10 to 5 tracer particles. And we solve Fokker-Planck equation for all those tracers. So this calculation is very heavy and very big. And well, yes, this is an assumption about the physical mechanism related to cosmic rays. For example, we assume reacceleration by alphonic turbulence, and we assume some dynamo. This is a relation between turbulence and magnetic field. And also we assume some injection seed population at z=1, where we neglect shock acceleration for simplicity. And where we can change, we can check if cosmic ray proton affects the result or not. And yes, this is a turbulent energy flux shown in this tracer method. And there is a merger happening between two galaxy clusters, and this injects a very strong turbulence inside the galaxy cluster. And we can follow the radio emission produced by those mergers. So basically, we follow the spectral evolution for all tracers inside the galaxy clusters, and then merger happens that produces very strong turbulence. And the turbulence reaccelerates cosmic ray particles, then radio emission becomes bright. So this is a temporal evolution of radio power. So we inject cosmic rays at this epoch. I mean, it's rapidly cooled by impulse component radiation. And then merger induces turbulence, and radio emission becomes bright. So keeps this kind of 10 to 24 watt per hertz power. And we can discuss, so one of the merits of tracer method is we can discuss very detailed modeling inside one galaxy cluster. So for example, this is a spectral index distribution inside one galaxy cluster. So this is a map of spectral index. And this is a histogram of spectral index of each mesh. So we consider the line of sight integral of radio emission, and we can measure the spectral index between two frequencies. So we can calculate spectrum of cosmic rays and also radio emission. So we can discuss something about spectral shape of those emissions. So we can discuss spectral index, of course. So there is a big difference between those two models. One is only electron model. We inject only relativistic electrons and assume the acceleration. And the other one, we assume cosmic proton at first, and that proton produces electrons, and electrons are reaccelerated by turbulence. As you can see, there is a big difference in the spectral index distribution. And in reality, I think this is a local observation every 2255. We can see a broad distribution of spectral index. So maybe the real case is much close to this one, but in more qualitative way, we can discuss the constraint on the amount of secondary electrons, of course. And another important proxy is primary point-to-point correlation between radio and X-ray intensity. This can be also done by, this is statistical work for single cluster. So we can make this statistical figure for one observation, one cluster. And if we inject only electrons at first, we see sublinear correlation. And if we inject only protons at first, this is almost linear, but in different direction, this is superlinear. So we can observe difference in the point-to-point correlation between X-ray and radio. So we can compare this result with observation and discuss the mechanism of cosmic injection inside galaxy clusters. So this is a summary. Thank you for listening.
Thanks. Questions for the speaker? There's one over there. Yes.
So very nice results. So my question was about the injection of particle in the simulation. So so far you assume just a single injection, and correctly you have to give a redshift that is very high redshift. But do you plan also to explore a different kind of injection during?
Yes, we can. Yes, this is a kind of example of work. In reality, maybe injection is continuous. And well, one assumption is it is proportional to the star formation rate density of the universe, which peaks at z equal to z equal 1. So maybe the injection is more previous, but well, we can assume some activity of AGN in central region. So we can tune the both injection epoch and position. So yes, we can test several story of those injection methods. Yeah.
Is the injection by stellar processes negligible with respect to the one of the GNs?
Sorry, what is negligible?
The contribution of stellar processes to the injection of relativistic. So it can be neglected.
Yeah. It's yes, because we can see some connection between, for example, radio and Asian radio jet, and well, it might be very important to. It's much important for diffuse emission. Asian jet is much important diffuse emission compared to galactic wind or ground pressure stripping from galaxies.
I can ask another one. Sorry, I didn't understand how the electrons get reaccelerated. I didn't understand. So what's the process that causes the?
Okay, it's a so-called second order Fermi acceleration. It's a interaction between wave and particle. So there is a perturbation in the electromagnetic field, and that resonate. There are two more, but in easier cases resonate with cosmic particles. So there is a phase velocity, and the phase velocity matches with the velocity of cosmic particles, and it feels constant electric field, and it accelerates.
And the perturbation is due to mergers.
Well, yes, and then the turbulence is generated at very large scale and decays into very small scale. Okay.
Can you make a prediction of the turbulent velocity that we should observe with a prism on a cluster radio?
Well, yeah, yes, that is a job for the MHD simulation, and yes, we need to, because grism observation is a little bit tricky because it's integrated one.
Yeah, but I think the simulation you can integrate the same way,
Yeah.
the same solution.
Yes, actually, yes, but it depends on the aperture size and maybe the turbulence inside that aperture size is not isotropic, and it complicates the discussion. So, well, it can be possible, yes, of course, but it's not a job for the tracer particle method. It's for the hydrodynamic simulation. So we should directly use that information from the hydrodynamic simulation. This is a post process.
Any other questions? Remotely? Okay, then thanks again.